another episode of Likable Science here on Think Tech Hawaii. I'm your host, Ethan Allen. Thanks for joining us this Friday afternoon. Today on Think Tech, I have Robert Jedicke from the Institute for Astronomy at the University of Hawaii.
Thank you for having me.
And well, welcome. I'm glad to have you here. And we're going to be talking about some really earth-shaking science, as it were, shattering stuff. The possibility of collisions with asteroids and Earth, and how this has been part of Earth's history and how it probably will be part of our future, right?
It's not a possibility, it's a certainty.
So we can give it enough time, right?
Not all the time. Asteroids hitting the Earth all the time. It depends on what size you're talking about.
Right. Little ones, we don't
Little ones happen all the time, right?
They're bouncing through our atmosphere all the time and crumbling to dust. And it's just the big ones that we have to begin to be concerned about. Robert was telling me right before the show that he has a background sort of varied a little bit. You were trained as a particle physicist initially, worked as a software engineer. So what got you into asteroids then?
Well, probably if you asked me back when I was in high school what I want to do with my life, I would have said I wanted to be an astronomer working in Hawaii. And the reason for that was because when I was about 16, they were building the Canada-France-Hawaii telescope on Mauna Kea, and I was, of course, reading the amateur astronomy magazines, and I still remember vividly this photo of them leveling the area on Mauna Kea for the Canada-France-Hawaii telescope. And I thought, wow, that would be a great place to work. And I figured out the timing of when it would start operating, and I realized, oh, that would be about the time when I could actually start being an astronomer. And so I thought, this is a perfect opportunity for me.
There we go, okay. But you took some side tracks before doing it.
Yeah, it turns out that the physics program at the university I went to required you to take one less course per year than the astronomy program. The astronomy required you to take physics plus an astronomy, and I wanted to play football. So I thought, I'll drop down to just taking physics, and so I could play football.
Okay, there we go. Well, you gotta have your priorities
exactly
straight different times. Excellent. So what is it that sort of keeps you? What do you love that keeps you sort of coming into work every day and sort of drives you in this work?
Well, I actually think that it's an interesting problem intellectually to think about asteroids that are in orbit around the sun that might hit the Earth someday, and I think it's actually one of the areas of astronomy that has direct relevance to humanity, right? If we actually live in a time when if we find the asteroids that are going to hit the Earth someday, we could actually do something about it. We could actually find these asteroids that are going to hit the Earth, recognize that they're going to hit the Earth, predict when and where they're going to hit, and then we could actually go out there and probably deflect it. And I think that's pretty important. I mean, the dinosaurs did not have that technology, and the dinosaurs went extinct.
All right, exactly. Yeah, no, there were some big things hit, and now at some size, we might not be able to do too much about it, or doing things about it might be potentially dangerous too. But it is intriguing that we actually we're on this very interesting sort of cusp where we've really only in the last decade maybe has that become a conceivable technology, right?
Absolutely. I mean, certainly deflecting an asteroid, that technology has only been around maybe for a decade or so. Yeah. And the technology even to find the asteroids at the rate at which you need to find them in order to identify them before they strike the Earth has only been around for a decade, and we continuously improve it as well. I mean, when I started off in this field 25 years ago, we only knew something like 10 or 20% of the largest asteroids that could wipe out humanity, wipe out civilization. And now we know 90 to 95% of them. Right? So in the space of just 25 years, we've basically gone from having almost no notice of a civilization-ending impact to basically knowing where all of those objects that size are, and knowing that none of them are going to hit the Earth.
Now, so how have you figured that we know where 90 to 95% of these are? I mean, aren't there what's the basis for that calculation? I mean, because there's stuff that you don't know that you don't know, as it were, to quote whatever that was.
The unknown unknowns.
Right.
That's the question I get asked a lot, right? And actually that is my exact specialty, what you're asking, right? Is how you quantify how many objects you actually know. And so, we use telescopes and digital cameras, but big, expensive digital cameras on big, expensive telescopes to try and survey the sky to look for these asteroids. And my specialty is to characterize the efficiency with which we use those telescopes and those cameras to find the asteroids, right? And so to make it very simple, I know that we have about a 90-95% efficiency at finding the asteroids. And so if we found 100 asteroids and we have a 90-95% efficiency, that means we know where 90 or 95 of them. But because I know the efficiency, I can also know how many we haven't found yet.
Okay, excellent. So you sort of survey patches of the sky, look how many things of X size you can see passing along there that are asteroids over what period of time, and you can begin to crank up the numbers then for larger areas of the sky over longer periods of time and all.
Exactly. I mean, of course, it gets very complicated very fast, right. And it's not just so simple as pulling red or blue balls out of a box, right? And knowing that there are 95 blue balls and 5 red balls, and that kind of a simple answer. Because the thing with asteroids is the distance to an asteroid changes with time.
Right.
Which means that the brightness of the asteroid changes with time. Right. It also means that the apparent rate of motion of the asteroid across the sky changes with time. Mm-hmm. So there's all these things, and of course the Earth is moving and we're on the rotating Earth, right? So all these things are changing all at the same time. So accounting for all those different efficiencies is quite complicated. So, but that is my specialty, and I spend a lot of time, many years of my life, working on exactly that figure to try and get the exact answer on how efficient we are.
So most of these asteroids that you watch are the so-called near-Earth asteroids, right?
Right. It's actually a term that was invented before I got in the field. I might have complained a little bit about it. But the near-Earth asteroids, I think, is a misleading term because it makes people think naturally that these asteroids are near the Earth. And in fact, these asteroids are most of the time not anywhere near the Earth. They're
large elliptical orbits.
They're in these huge elliptical orbits, and they go around the sun. They don't go around the Earth. So there are some objects that are classified as near-Earth asteroids that can be 5 times further away from the sun than the Earth is, and we still call them near-Earth asteroids because at some point, at some time in the future, that asteroid may come in to the inner solar system and happen to get to a point in its orbit when the Earth also happens to be near that point, and then you can get a collision, right? So it's the potential for the future opportunity to be near the Earth rather than their actual location right now.
Right, yeah, okay, that makes sense. But then there are other classes of asteroids, right?
Oh, sure. There's many different classes of asteroids. The 2 big repositories of asteroids in our solar system are the main belt of asteroids. So you have the planets going outwards from the sun. You've got Mercury, Venus, the Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And in between the orbits of Mars and Jupiter, there is what we call the main belt of asteroids, which is also a bit of a misnomer. It's more like a donut. There's a donut-shaped region of space out there between Mars and Jupiter that has about 1 million asteroids in it, larger than half a mile in diameter. Wow. And there's another similar sort of donut-shaped or toroid-shaped area or volume outside of the orbit of Neptune, which is called the trans-Neptunian region. And Pluto, which used to be considered a planet, is now just known to be a large asteroid, or some people would call it a dwarf planet. Pluto is one of the largest members of that belt of asteroids that are out beyond Neptune. And there's also a very large number of millions of asteroids out there.
Okay. So, and then there are occasionally, I guess, random chunks of rock, as it were, coming from unknown places, right?
So the main belt of asteroids in that trans-Neptunian region, most of the asteroids in those regions have been there since nearly the time of the formation of the solar system, 4.6 billion years ago. So most of them have been there, and they've been sort of in stable orbits, and they're not doing anything. But every once in a while, some of those asteroids collide into one another, or there are subtle gravitational and also these what we call non-gravitational forces that happen that can sort of nudge the asteroids out of their stable orbits and put them into a kind of a condition with Jupiter that we call a resonance. And a resonance with Jupiter is kind of like pushing a swing. You know how you've got a child on a swing, and you just tap the child, maybe with just a finger or two, right? But if you just tap them at exactly the right rate you can build up a very large swing in a child, right? And it's the same thing with the asteroid. Jupiter basically taps. Jupiter's large gravity can tap on those asteroids very regularly every few years, and just that little tap can drive those asteroids from their nice stable orbits in the main belt into these near-Earth asteroid orbits.
Okay, yeah, into a big,
Right.
yeah, big.
And the same thing happens with the belt of asteroids that are out beyond Neptune. Those asteroids out there can collide as well, and they also have these gravitational effects. And some of those asteroids also get driven into the region between the large planets. And when that happens, those asteroids are called centaurs. Right? So we have main belt asteroids, we've got the trans-Neptunian asteroids, and the centaurs, we have near-Earth objects.
Okay. But so, bottom line here, what are the odds that a big chunk of rock is going to hit the Earth at any given time?
At any given time. So the odds that a big chunk of rock is going to hit the Earth are 100%. Right?
Okay,
A big chunk of rock is going to hit the Earth.
Right.
Okay.
It's happened before, and it will happen again.
It happens many times, right? The question is, when is it going to hit the Earth, right?
So say within the next century.
So within the next century, if you're talking about one of these civilization-ending impacts, something that would actually wipe out all of the people on the planet, we now know that the odds are almost zero, right, that it's going to happen in the next century.
Okay.
But when the century first started, say 20 years ago, the odds, there was only about we didn't know where most of the asteroids were at that time when the century started, right? So it's actually really amazing that we've reduced the probability of an unknown impact by a dramatic amount, right? So now we know that none of these large impacts are going to happen in the next 100 years. However, because asteroid orbits change with time, because of the influence of the gravity of the planets and these non-gravitational forces, those forces can very slowly change the orbits of the asteroids. And also you can have new asteroids that hit one another in the main belt of asteroids, generating more near-Earth objects. So that kind of timescale happens over a few 100,000 years or something like that. So the way I would say it is that in the next 1,000,000 years, there's an extremely good chance that a large asteroid will hit the Earth.
Okay, well, I don't intend to live 1,000,000 years, so. Yeah, and so we know to some extent what some of these big impacts do, right? I mean, we have geologic evidence on Earth, right? The big crater down by the Yucatan, right?
Sure, I mean, that's the most famous one.
Right.
We know of something like 150 or 200 different major craters on the surface of the Earth that were caused by asteroid impacts. I mean, if you look at the surface of the moon is covered
Pockmarked, yeah.
with craters. I mean, at every different scale. You can look at it on the largest scale. I mean, with your naked eye, some of the little circular features you see on the surface of the moon are impact craters,
right,
or the remains of them. And no matter how close you get to the surface of the moon, you're going to see impact craters.
Right.
Even if you're standing right on the surface of the moon, there will be little 6-inch diameter craters on the moon caused by little pea-sized pieces of rock that hit, right?
Right.
So the moon is just covered with craters. And the Earth would be covered with exactly the same sort of craters if it weren't for the fact that we have an atmosphere, and 2/3 or 3/4 of our world is covered in oceans.
Right.
And we have plant life and wind and erosion. But yeah, so we know of 150 to 200 impact craters, but yeah, the most famous one is this one in the Yucatan Peninsula, which was created 65 million years ago when the dinosaurs went extinct.
Right.
And so we're very, very confident that asteroid impact 65 million years ago wiped out the dinosaurs.
Right, and that was how big was that object, do they think?
It was about 6 miles in diameter, right? So, and to put that in scale, right? I mean, Mount Everest is, the tallest mountain in the world when measured from sea level to its summit. Mount Everest is about 6 miles high, right? So we're talking about something the size of Mount Everest striking the Earth. And the other thing to keep in mind is that when an asteroid strikes the Earth, it does so not just at a gentle pace, right? It's moving at a speed that's about 100 times the muzzle velocity of a high-speed rifle. So you have something that's the size of Mount Everest moving 100 times faster than the fastest bullets.
Right. And I'll tell you what, on that sobering note, we're going to pause and take a little break. You're here watching Likeable Science. I'm your host, Ethan Allen. Robert Jedicke from the Institute for Astronomy at UH is with me. We're talking about the probabilities of collisions with asteroids and Earth. And we'll be right back after a short break.
Welcome to ThinkTechHawaii.com. This is Johnson Choi, your host. My focus is Asia in Review. We talk about interesting subjects in Asia. Be sure to check the thinktech.com website on the next topic. Thank you.
Hello, I'm Marianne Sasaki. Welcome to Think Tech Hawaii, where some of the most interesting conversations in Honolulu go on. I have a show on Wednesdays from 1 to 2 called Life in the Law, where we discuss legal issues, politics, governmental topics, and a whole host of issues. I hope you'll join me.
Aloha. I'm State Senator Russell Ruderman. I represent the Puna and Ka'u District on the Big Island and the host of Ruderman Roundtable. We're here on Think Tech Hawaii every other Tuesday at 2 p.m. You can join us at thinktechhawaii.com. You can find a link there to a page where you can see past episodes. And we talk here about good government, environmental issues, and issues of the day facing the state of Hawaii. I'm Russell Ruderman. Please join us for the Ruderman Roundtable. Mahalo.
And you're back here on Likeable Science. Thanks for joining us again. I'm your host, Ethan Allen. You're on Think Tech Hawaii. Joining me today in the studio is Robert Jedicke from the Institute for Astronomy at University of Hawaii. And we're talking about asteroid collisions. But before we get into that, I want to take a little aside. As regular viewers of the show know, I typically like to tell a little campfire story, interesting things about science. This isn't exactly on that line, but it's something sort of close. As some of you know, I study water, and I was recently reading a little infographic about the indirect uses of water, how much water it takes, for instance, to make a glass of wine, which is about 30 gallons, how much it takes to make a cotton t-shirt, which is 700 gallons. And they brought up a very interesting comparison there that I found memorable, that if each day during the course of a year, you forego 1 glass of milk and instead drink 1 beer, over the course of a year, you will save this planet 15,000 gallons of water. So, take from that what you will. Anyhow, we're back here, going on to much more high-level stuff.
May I just say that
sure.
I don't think there's any beer on asteroids, but there is water in asteroids.
Okay.
And actually,
right.
if you have time at the end, you might ask me about water and asteroids, because I'm actually involved with a company that is trying to mine asteroids for water.
Oh, interesting. Yeah, because it used to be said the moon had no water on it. Now they found actually substantial stores of water on the moon, right? Yeah. Huh. Intriguing. So we do have a video showing a bunch of asteroid motion here, I believe, and we might. Oh, and why don't you explain what this is? What we're going to be seeing here then?
So this is a video I created, and it shows it's a simulation of the motion of the 1,000 largest near-Earth objects. So these are 1,000 asteroids. Yeah, this is what we're seeing right now. This is 1,000 asteroids. Each of the green little blobs there represents a near-Earth object, the largest 1,000 of them. So these are objects larger than about a half a mile in diameter. And the video is created in what I think is an interesting way. So imagine if you're in a race car, a Formula One race car or something, and you're going around a track. And imagine there was a helicopter above the race car, just following the race car going around the track. And it had a camera looking down at that one car, right? So the helicopter is constantly going around on top of this car. And then you saw all the other cars swerving around it. So if a car was coming up fast and taking the inside track, you'd see it, passing in, and similar on the outside. Or if your car that you're following was moving faster, would pass other cars. So that video is showing exactly the same thing. That the Earth is centered in the field of view, and we're watching all the other asteroids passing around it, right? And sometimes if you could look at that video, you would see some of the asteroids appear to do sort of loop-the-loops around the Earth, or come very close to the Earth and then back away. And that's because of the same sort of thing, that sometimes asteroids are moving faster on an inside track on the Earth, and so they catch up to the Earth. Sometimes asteroids are on an outside track and they're moving slower, so it appears the Earth is passing them. And but it gives you the idea. The reason I like this image, or this simulation, is that it gives you an idea that we live in a dangerous sort of a pinball game, right? Where the Earth is surrounded by all these asteroids, and they come close to the Earth on a regular basis. And it's just, when you look at this, it really gives you this impression that we live in this sort of this pinball game, right? And it's just a matter of time until we get hit by one of these objects.
Right. This is why when you see that, you realize, sooner or later it's bound to happen. There's no doubt about it. And just the question sort of is when. And so, what kinds of technologies are now being thought of to to take care of this. If we see one coming at a reasonable distance away and realize it's scheduled to hit Earth, what kinds of things can we do about that?
Yeah, the technologies are really amazing, right? Right from the finding the asteroids to how we might deflect them. Every 2 years, people laugh when I tell them this. There is what we call a planetary defense conference, right? Where people from around the world get together to discuss all these issues.
Okay.
And I think the last time I was at one, there was probably 100 to 150 scientists from around the world, and also including people from, say, FEMA, right? And from the government, from NASA, scientists from Los Alamos, where they can do computer simulations of atomic bomb explosions and how to deflect asteroids. And plus you've got the scientists like me who spend their time trying to find ways to more efficiently detect asteroids. So, the technology we use to find them is very interesting. We've used large telescopes. Right now in Hawaii, we actually have the best system for finding near-Earth asteroids, these ones that could hit the Earth. It's called Pan-STARRS 1. It's on Haleakala. And it is currently the world leader in, by far, of finding these dangerous asteroids that are coming close to the Earth. That telescope has got a mirror that's about 60 inches, 70 inches in diameter, and that's a really big mirror, right?
Sure.
And we have at the time when we built it, it had the largest camera in the world in it. It had a 1 billion pixel camera on it, right? You think about your little digital camera has got maybe 10 megapixels, right? Our camera had 1 billion pixels in it. And it cost, something like $10 million to build, right? And you couldn't put it in your pocket. This is a camera where, it's the size of the actual focal plane, the place where the detectors that are actually detecting light are about the size of a chessboard or something like that, right? So this is an amazing piece of technology that's currently being used to find these asteroids. And we're thinking right now of trying to design bigger systems, better systems for finding asteroids in the future. There is a new project being built in Chile that should be operational in maybe 5 years called the Large Synoptic Survey Telescope. That's going to have a mirror that's more than it's about 9 yards in diameter. And it's going to have a more than 3 billion pixel camera, right? So again, it's hopefully going to be used to be finding asteroids. So the technology we use to find the asteroids is incredible. But you asked how we might deflect them, and people right now at this Planetary Defense Conference are arguing, I would say, about what the best way is to do it. Some people advocate for something called a gravitational tractor. Other people advocate for slamming into it. Other people advocate for blowing up a bomb next to it.
Yeah, and each one, it's one of those interesting things. You don't have a lot of test ground for this, right? I mean, you're going to try that technology out when you need to use it, and probably not really much before, right? I guess I've smashed a object into a comet to look at impact, but that's only a crude approximation of what you're talking about.
Right. Yeah. Of course, we've landed, or NASA and other space agencies around the world have landed and rendezvoused with asteroids, planets, comets. So we know how to get to those objects, and we know how to land on them sort of gently. But that's actually a different problem than slamming into it fast, right? If you want to, say, slam into something fast, then you've got, as I said, these things are moving at 100 times the muzzle velocity of a bullet. You're trying to hit something that's moving 100 times as fast as at that speed with another thing that's moving at that speed, and trying to do that is extremely complicated.
Yes.
Right? And in fact, yeah, you're right. NASA has only done it once, although they were spectacularly successful that one time that they did it.
But so that is, some people, as I understand it, think you want to hit the thing gently and just sort of push it aside a little bit to just change orbit slightly, or blow a bomb up next to it to try to nudge it out of its dangerous orbit. Other people want to try to knock it apart or tractor it away, you were saying?
Yeah, I think that the sort of the person who doesn't do this thing, doesn't think about this stuff regularly, would think about, oh, well, let's just blow it apart, right? But then instead of having one bullet hit the Earth, you have buckshot hitting the Earth, right? And that's not a good thing either.
Unless you can guarantee that it's all going to be a very small part.
If you could, yeah, but you can't guarantee that, right? So there's no way to guarantee that you basically make it all into dust. If you could make it all into dust, then you might be okay. But if you just created, instead of having one chunk that's 1 mile in diameter, you had 10 chunks that were 1/4 mile in diameter, that would not be very good.
Right.
So, you know, my personal favorite idea is something they call the gravitational tractor, which is not a tractor beam like on Star Trek. People, I think, know what the tractor beams are. You know, in Star Trek, you've got the Enterprise. It's got some other thing that they put the tractor beam on, it sucks it close to it, right? Like sort of creating gravity. But that's not what the idea of the gravitational tractor is. But in the gravitational tractor idea, what they do is they have a gigantic asteroid here, and they have the tiny little spacecraft here, right? But it turns out that, you know, in the universe, the asteroid will attract the spacecraft, so the spacecraft would fall towards the asteroid.
Right.
But at the same time, the little tiny spacecraft is actually attracting the asteroid, so the asteroid is actually falling to the spacecraft.
Right.
So what they do is they exploit this idea to try and basically use the gravity of the spacecraft and little rockets on the spacecraft to keep the distance between the spacecraft and the asteroid constant.
Keep dragging
And so you
it.
basically drag
Right.
the asteroid away. And the reason I like this idea is because it does not depend upon the internal structure of the asteroid. It doesn't depend on whether or not the asteroid is a single monolithic chunk of rock, or if it's just sort of like what we call a rubble pile, or if it's got ice in it, or if it's made of iron. It doesn't matter how fast it's rotating. It doesn't matter the shape, right? This technique works regardless of all these techniques. Plus, it only requires us to have a spacecraft that's sort of following around, which we know how to do. Hitting the asteroid and blowing stuff up is something we don't yet know how to do.
It's not nearly as exciting.
I agree. Right. And that is just my pet idea, and that is my favorite idea of all the ones that are out there right now.
Excellent. Well, this has been most informative and enjoyable. I've really learned a lot, and I have a better view now of the dangers we face or don't face. And I think this is a great thing you're doing. I can see why you like to do it. So thank you very much. I've very much enjoyed having you on the show, and good luck with your continued research.
Thank you very much. I'm going to be out there protecting the world.
Excellent. Take care. Aloha. And we'll hope you'll see you next week on another edition of Likeable Science.